So this is for ME128, spring 2016. I was supposed to do this 2016, 2017. This would have been your lab 2 if the large wind tunnel was still working. What I did was model an airfoil and then a test chamber, and then I ran a Solidworks Flow simulation. I know a few of you are interested in learning how to do this, so I figure I'll share what I'll do, or what I did to get to this point. I'll show you the finished result right now. I have a pressure contour for a 19 meter per second flow inlet condition. Walls are just real, no roughness, and the outlet is to atmospheric. And then I have flow trajectories for the fluid velocity, which you can see interact right here, and then flow above and below. And we can mess with the settings. I'll explain more to that as we do this. So let's go to the beginning and get the airfoil. What you need to do to get this shape into SolidWorks is actually import a spline curve. And so you're given coordinates, and what you can do is just, for whatever airfoil shape you're looking for, I went to this website, airfoiltools.com. You can find any shape that you like. They give you all the curves. Specifically, they give you the coordinates, which is what you'll use to get them into here. This process requires you to take these coordinates, which are XYs, and then move them into Excel. So we'll do that really quick, just so you know what that process looks like. So you just copy and paste. You have 2 columns. In this case, it's 1 column, and so you have to do a conversion to 2-column format. What you can do is in Word, and there probably is an easier way to do this. I just figured this out on my own. Insert table from the conversion. Just leave it auto. It's easier this way. You don't need to mess with anything. Copy and paste this over to Excel. We'll get rid of this contents. Paste this, and then we just needed to do some data manipulation to get it to look nice. So we'll move this over here, and then we'll move these down here to this column, and then we'll move these over to here, and then we'll get rid of the extra data. Isn't too bad. Now the one thing you need to keep in mind is that in SolidWorks, it wants a Z coordinate, so for thickness. We don't really care about thickness at this point. That's for 3D curves. Oops. So you'll just insert a 0 column, the same number of rows. That's what you have. And then save this file. So what we'll do is we'll go to wherever you want to save it. You have to save it as a text file, and there's kind of a tricky way of doing it. We'll do airfoil test. Save it as a formatted text space delimited file, a .prn. This will keep the column data. Close this. Don't save. And then if we go back here, we can see here, all we're going to do here is just change the file extension to .text, ignoring any warning that SolidWorks gives us. And then let's go to, this is for the same one, but let's just make a new part. Curve through XYZ, browse for the file we just made, select text files, whoops, text files, airfoil test, click OK, and it's going to be really, really, really small. The way SolidWorks does it is it does it on a millimeter basis, and so if you need to scale this, obviously we can do that. Just insert a sketch on that face, which is the front plane. It'll zoom in on this, and then you can convert this entity to a sketch. It's not closed. There's an opening over here. Close this off, and there's a whole method for design of tail, what you want these edges to look like. We're just going to close it off to join these 2 points. And so we have a sketch. If we want to scale this, we can go to Tools. Actually, I think we need to exit the sketch first. No, it's Sketch Tools, and then we go to Scale, and we can scale this about the origin. We want to select the spline to scale, and then scale about the origin, which it's not letting me do. So let me select this, and then scale about the point. There it is. Okay, and then what I did was I just made a line from here to the midpoint of the line I created to get the arc length, or not the arc length, but the actual length of the airfoil. And so I scaled it up 25 times. So I'll make it really big. So now we have a sketch that we can extrude. Our scale's in millimeters, and so I believe I made mine 600, not 6,000 millimeters, midpoint, and this is where you want to be conscious of what you're doing, because you're going to be joining 2 bodies, the test chamber body and then this airfoil body. And so doing a mid-plane extrusion will make everything easier. So there's our airfoil. I may have messed up the scale. It's fine. I don't intend on using this piece. For you, when you're making this, be careful about what your lengths are. Do measurements, and then just think about if that's what you'd really be seeing. So let's get rid of this. Not going to save that. This is the airfoil. Same process. For the test chamber, what I did is I just made a square and extruded that. So let me show you what that looks like. Geometry only. So I made this out of aluminum. All my bodies are made out of aluminum, which if you want to do any sort of material study, you can. I just made it out of aluminum because that's what we have on campus. So my first box is just a 700 by 700 millimeter volume. I cut a 695 by 695 square through the body, so I would have 5 millimeters on each side, which gives me a box with 2 holes in it, so you can imagine air flowing through it. And then Solidworks Flow requires lids to specify boundary conditions. You can't just throw that body into Flow. You have to make sure that it's a closed volume. And so I just made lids. SolidWorks has a lids tool, so I don't think I need to go into that. This part is actually relatively simple. Just be careful about what your system conditions are if you're not using a box. If you're using any sort of complicated geometry, making a lid is something that might be a little bit more interesting, but for this case we have something simple. Joining these 2 is done with a mate. So let's get out of SolidWorks Flow. I want to hide these. And I want to go to this. So you drop your 2 bodies into the assembly. And then if you do every, in this case, if you make both of these bodies the extrusion from the midpoint, your origins are going to be right in the middle. So you can actually just mate on their origins. You kind of have to be clever and think ahead about something like that. So if you have any sort of complicated shape or geometry, be careful about what your mates do. But as long as you're careful, you'll be fine. Mating them on their origins puts it more or less in the middle. So there's some symmetry there that makes calculations a little bit easier, wherever symmetry exists, that is. And then from there, if you're on campus, you already have Solidworks Flow. If you're at home, you need to enable it in a premium add-in. And it's under add-ins, and then you just select Solidworks Flow, and it'll open it. So now we have our shape. Let's do a flow study. And you can use the wizard to get the initial conditions started. So you have project name, you can name it whatever you want, whatever your unit system is. This is an internal flow, and we want to exclude cavities without flow conditions. In this case, there's no cavities that we really care about. For some, if you're doing senior project, you might have something you want to specify. For gases, we have air. If you want to do anything with water, they have water as well. Anything, almost anything you really want to look at, you can do in here. They have their own densities. It's all defined. If you want to define your own densities, you can do that. Just be careful with that. We won't go into that though. If you go into the next step, and let's just specify this, you can select the flow type, laminar and turbulent, or turbulent only. I just leave this as laminar and turbulent, and maybe that's wrong. I let the software figure out how these fluids are moving. Your wall conditions are adiabatic. You don't have any heat transfer coming in unless you want that. And then roughness 0. If you care about roughness, we can look at that some other time. Keep your thermodynamic parameters within what they should be for whatever your experiment is. Try to keep it consistent if you can. And that gets your initial conditions in. At this point, you need to specify inlet and outlets and then walls. So if we go to flow simulation features, you can also go to it from here. Looking at the project, we need to insert boundary conditions, and you can do it from there or right here. Insert a boundary condition. Let's look at the inlet side. So we'll select other. We want to select the inside face of this lid here. So we do select other, select that inside face, select an inlet velocity condition. We'll do 19 meters per second. That was one of your data points. You can select it as fully developed, and that's something you may want to do. I'm just going to leave it alone. There's thermodynamic parameters here, turbulence parameters. If you don't understand what these numbers mean, it's okay. They will change the way the fluid behaves. Obviously, it's turbulent. I would say leave everything as default, and you'll be okay for now. Boundary layers turbulent. This is where simulation can get complicated. For this case, let's just keep everything simple. So we have our inlet velocity. Solidworks gives us a nice little graphic, tells us it's flow going in that direction. Let's specify a outlet condition. The way we do that is we're basically going to say that we're venting into atmosphere, so we don't have to specify an outlet velocity. We can do that if we want to. I think it's more useful to just specify this as atmospheric pressure on the other side. So similarly, select other, select that inside face. I accidentally selected that other one. Get rid of that one, and then choose the pressure opening, environment pressure, Let's just go into atmospheric. So now we need to specify walls. So when you're doing simulations, you have to think, all right, where am I interacting with things that I care about? Stuff like the airfoil you don't need to define unless there's a certain condition, but for the space that we're modeling, I'd like to just specify the wall conditions. And so we'll insert a boundary condition, we'll insert a wall, a real wall, and we'll select the inside face of everything, all of these. Okay, and then so we have our 4 walls defined, real walls, no roughness. We don't need to worry about heat transfer or anything. If we wanted to do that, we could, and it's useful to look at for certain projects, but in this case we don't really care about that. Okay, so I think we have everything we need to run. We'll do a new calculation. Depending on your computer, this may take a minute, this may take 15, but we'll run it. Solidworks will let us know when it's done. This is where you get some coffee. And so we're done. So now nothing's loaded in. We need to tell SolidWorks what we want to know. So we'll do a cut plot. And generally it does a mid-plane cut plot with a certain thickness to get the calculation. So let's display contours. We'll do it for pressure. And we'll do, let's just do 50. We can do a 3D profile. I'm not going to really go into that right now. I just really want to see if we're looking at what this is giving us. It's a plane with pressure contours around that airfoil. And so you want to think about what you'd expect to see. You want to see areas of high pressure towards the front where the fluid is hitting the airfoil. And then you want to see pressures drop below and raise above, or some configuration of that depending on the angle of attack. So let's do that. And so now we have a cut plot for pressure. And so you can see, we can see the stagnation point, pressure, how these how your fluid is interacting with the airfoil with respect to pressure. Let's see what it does with respect to velocity. We can do a flow trajectory, and we have to choose a seed point. We'll choose on the inlet side, select other, select that inside face. Oops. Select. Okay. Delete that one. We'll do 50 points again. You can do whatever appearance you want. I like lines. We'll make them thin, and we want them to display a velocity. And we'll go over scaling in a second. So we have our velocity of the fluid. If we want to do an animation, we can play that. So we have a lot of red. So that means our scale is weighted towards that top end. So let's take a look at that. If you double click on this, it should open up, oh, it's right here. It'll open up the scale, and you can change it. In this case, we don't really have anything near 0. There's no blue. So let's raise that bottom limit, and we'll go up to, we'll say 19. That's the minimum it could possibly be at with respect to the inlet, but it might slow down around the airfoil, so we'll do that first and see what happens. Okay. that's better. Now we're kind of in this green zone. So we're in the 20s, or 20.1 to 20.7, I would say. We do go down to 19 though. So let's go a little bit lower and a little bit, or a little bit lower on the high end and a little bit lower on the low end, and just try and capture as much of this data as we can. So we'll go to 18 on the bottom end, and we'll go to 20 point. Let's do 20.8 meters per second. So that's better. You can see right about, it jumps, slows back down, we go down to blue, so we know we're getting some 18s, which is what we would expect. You need to make sure that your scale for whatever you're looking at is set correctly. That way you're not just looking at all blue, all red, or you're not capturing the entirety of the data. You want to see how this fluid's behaving. So that should get you started. This is for a 0 degree angle of attack. What you can do is make a reference plane and then specify an angle of attack that way. And so I'll let you guys do that one. And that will change the pressure characteristics and the velocity too, which would be cool to look at. If you need any help, you have my email. Send me any questions you have. If you want these files, let me know, and I can get them to you. So I'll see you on Monday and Wednesday.